Writing a vector given its magnitude and direction angle. Remember, a vector is defined as a directed line segment starting at the origin and ending at some terminal point. So let's start by drawing that vector. And a vector can appear in any quadrant. By drawing it in the first quadrant, it just makes the drawing a little bit easier and makes it a little bit easier to generalize. But we have some vector, and we know the magnitude of that vector, and we know the direction, and what we're asked for is where is that terminal point xy. Much like in finding the magnitude and direction of the vector, we can drop a perpendicular line down, a vertical line down from that point to the x-axis, which will give us a right triangle, and we can solve the triangle. Remember, the magnitude, this guy over here, is the thing we know. X and y are the things we are looking for. So we recognize that y is the opposite side and the magnitude is the hypotenuse, and opposite over hypotenuse is sine, so sine theta equals y over the magnitude. Or rearranging that, we get that y is the magnitude times sine theta. And similarly, x is the adjacent side, so adjacent over hypotenuse is cosine. Cosine theta is x over the magnitude of the vector. And rearranging, we get that x is the magnitude times cosine theta. Right. Just using the properties of right triangles that we are already familiar with to find some general formulas. So, if we are looking at a particular vector where we know that the magnitude of the vector is 92, let's give some units to that, 92 meters per second. And the direction of the vector is at an angle of 203 degrees in standard position, then we should be able to figure out the component form. First thing I recognize is that a 203-degree angle is going to be over here in the third quadrant, which means that my x and y values should both be negative. But going in this direction, generally speaking, I can trust my calculator to handle that for me. So I'll know that x is the magnitude times the cosine of theta, which in this case is 92 times the cosine of 203 degrees, and making sure that my calculator is in degree mode, I get that x in this case is negative 84, let's round that to 84.7. And the units are in meters per second. Similarly, y is the magnitude times the sine of theta, which means 92 times the sine of 203 degrees. And again, making sure my calculator is in degree mode, which I know it was because I just did that for the last one. I can punch those things in, hit calculate, and I get that y is negative 35.9 meters per second. All right, so those are the components of the vector. And we could write the vector now in component form and claim that v is negative 84.7, comma, negative 35.9 meters per second. There is another way of writing vectors that is fairly common, and that thing is called unit vector form. Some people like unit vector form because it allows you to be a little bit more flexible in how you write out the vector, but it's really going to give you the same thing. So instead of calling a vector in brackets x comma y, what we do is we name the vector as x I plus y j. All right, I and j are literally just telling you this coefficient is the x component or the y component of the vector. That's literally what I and j are telling you about. And there's a couple of other nifty properties that I and j have that are beyond what we're going to have time to talk about this semester. But in this context, we can write the same unit vector. I'm sorry. In this context, we can write the same vector. So instead of calling it in component form, we can have negative 84.7 meters per second I plus, or I guess it would be minus 35.9 meters per second j. Again, pay attention to what the problem is asking. If the problem is asking for component form, use the angles, or use the angle brackets. If the problem is asking for unit vector form, use I and j.